Imagine hundreds of Telecom backup batteries helping to keep Finland's power grid stable. When frequency in the Nordic grid begins to drift away from 50 Hz, this could have happened. But these telecom-based stations across the country quietly react. Their backup batteries start discharging, not because of a blackout, but to stabilize the national grid. This is not a science fiction. This is a distributed virtual power plant. Our project focuses on analyzing the health of those batteries.
In Finland, the transmission system operator Fingrid maintains the grid stability. One of its key balancing mechanisms is automatic frequency restoration reserve. During upregulation, flexible assets must rapidly reduce grid consumption. There's where ELISA comes in. ELISA aggregates backup batteries from Telecom base stationed into a distributed virtual power plant. Instead of building new generators, they use existing battery systems to temporarily power telecom loads, reducing demand from the grid when needed.
It's brilliant, but there's a catch. These batteries were originally designed for backup power during outages, not continuous grid balancing. Frequent micro-discharges accelerate degradation, and here lies the core challenge. If battery state of health is overestimated, the company risks overcommitting in balancing markets and facing penalties. If underestimated, they replace batteries too early and lose revenue. Yet, state of health is not directly measurable in the field. So how do we monitor degradation across more than 1,000 distributed battery sites using only imperfect telemetry data? That's the problem we solve.
We worked with over 30 gigabytes of telemetry from more than 1,000 sites across nearly 2 years. Before any analysis, we built an automated quality pipeline to detect and remove physically impossible readings such as frozen sensors or unrealistic jumps. Then the core idea is to estimate aging using Coulomb efficiency, which measures how much charge a battery returns compared to how much it receives. If a battery slowly becomes less efficient at returning charge, that indicates internal aging process.
So, we built a structured pipeline. We first classify each data point as charging, discharging, or idle. We group consecutive points into segments. Then we are pairing each discharge segment with the charge segment before it. We're using Coulomb counting to calculate ampere hours for each segment. After that, we're computing Coulomb efficiency for each pair. We're then smoothing the results over time to detect long-term trends. Instead of analyzing individual noisy events, we track long-term trends across thousands of microcycles. Random fluctuations cancel out and aging accumulates.
Let's see the results for 14 sites, which actually mean more than 8 million rows of data. 12 out of 14 sites show statistically significant degradation. Site-to-site variation is moderate and consistent. The fleet average Coulomb efficiency decline is minus 0.89% per year. This number is realistic and consistent with what is generally reported in the literature for lithium iron phosphate batteries operating under mild duty cycles.
However, in more intensive grid applications, especially systems providing multiple or deeper cycling services, annual degradation rates are typically higher. Our batteries are in different geographic locations from 2 different vendors, and they are installed under different conditions. Yet, the majority show the same downward trend.
This framework helps ELISA bid more safely, avoid penalties, and plan maintenance better. By tracking battery health accurately, batteries last longer and revenue is protected. In short, we turn operational data into clear health insights, helping telecom batteries reliably support both the communication network and the power grid.